Okay, so let's have a look at this then. So what we're going to spend some time looking at now, portfolio task 1. We've got 2 tasks to complete, as it says on the work scheme. The first one is to do with beams, doing a loaded beam analysis using mathematical software, Autograph, which involves doing some calculations, and also using MD Solids, which is a software package that will actually just plot the stress forces and the bending moment diagram for the beam, the loaded beam. So let's have just a quick look at the portfolio task, which you've not actually been given yet, but you'll get as you go on site, on the UCS site very soon, and you'll be able to look at it after half term. So if we just look at it, the task that's involved, we've got the software MD Solids 3.5 will be available, and it can be used to explore the shear forces and bending moments experienced by a beam. We've already looked at the idea of stress diagrams and bending moment diagrams last year, so we're sort of using that really. And actually, as an extension, we can use calculus, and that's what we're going to do, to predict the exact shape of the curves, and hence predict the stress or moment at any point. So rather than, as we did last year, sketch what the thing looks like, we're now actually going to come up with a function that describes exactly what's going on. And below, the task is just set out in more detail, so it's absolutely clear what you've got to do. Produce your own example of a beam loaded with point forces and UDLs, uniformly distributed loads. And it's up to you what beam you analyse. I'm going to go through an example in a few minutes, and you'll probably do one similar. Sketch a shear force diagram for the beam and derive the functions that describe how the shear forces vary along the beam. So that involves calculating the reaction moments, the reaction forces at the supports, and we'll have a look at that in a minute. Plot the shear force diagram using graph plotting software, Autograph, noting the values of the shear forces at important points along the beam. So we're going to need the functions for each part of it so we can plot it, and we'll look at that. What's the equation of the line for each bit of these forces? Use calculus to derive the functions for the bending moment along the beam. That will involve integral calculus, because actually the bending moment is to do with the area under the shear force diagram, as we talked about. And the area is found by integrating, so we can integrate the function. And then we can plot the bending moment diagram. So once we've integrated it, we'll come up with a function that describes how the bending moment behaves, so we can literally plot it, noting the values of the bending moment at important points along the beam. Then, for the second part of the portfolio, you use MD Solids to explore this beam. So you put this your example into MD Solids here, and plot the shear force and bending moment diagrams using MD Solids, and then compare the curves. You'll have done it on Autograph, you'll have done it on MD Solids, they should match. In addition, you may explore the MD Solids software further and briefly outline the features of the modelling software, so you can then have a look at what else MD Solids can do. As an extension, the bending moment diagram shows points where the moment is zero, i.e. where it cuts through the beam or through the x-axis. Points of zero moment occur at the supports by definition, and MD Solids will show the positions of any other points where the bending moment is zero. Use mathematics to calculate the positions of these points, so that's an extension, particularly for the maths of it. We're going to look at an example now. So here's the example we're going to look at, and you've got it in front of you. And we need to produce the shear force diagram, which is this diagram here. This is the shear force diagram. And so it's been plotted in Autograph. So we need to be able to plot what's happening to the force between these 2 points, between 0 and 2. So we need the equation of this red line here, so we can plot it on Autograph. And we only need to plot it between these points of 0 and 2. and then what happens between the points 2 and 5, and so on. So we're going to have to take each part, point along here, and then work out how to use autograph to plot that. And then when we've done that, we can use integration to find the function that describes the bending moment, and again use autograph to plot it. So this is the bending moment diagram underneath. So the aim is to actually come up with those diagrams and use the software to do it. Okay, I'll do it by example today, and I'll ask you to fire up autograph, and you can actually try plotting this example as we go along. This might be a good idea, a good point at which to actually fire up autograph. So I've also given you my workings for this example. You may or may not be able to read my writing, so you've got that to refer to, but we're going to go through this example now. So this is where I was actually working out the answer to this problem and coming up with the functions for the stress curve rather, and the bending moment curve. But we're going to go through that now. So you can either make these notes as you're going along, or try and make sense of it as I'm talking it through this example, and maybe just add your notes to that. It's up to you. So the first thing we've got to do with this is to work out what the reaction forces are at the two supports A and B. So let's do that. The sum of the moments about A. So we've got moments acting clockwise this way, and moments acting anti-clockwise about this support A. And because the thing's stationary, those moments must equal 0 because it's not moving. So that this is a shorthand way of saying that all the clockwise moments and anti-clockwise moments must be cancelling each other out around A. And then by convention we set a particular direction as being positive. So if we're looking at this particular example, well, most of these forces are going to be trying to turn this thing clockwise around A. So let's take forces in the clockwise direction as being positive. I'm not sure which way I did it in my example. I might have gone the other way. Doesn't matter. I went the other way, did I? Right. In that case, let's go with that, otherwise we could get confusing. So what we do is we say, starting at this end of the beam at the support A, which is this point here, we travel along this direction and we look for the forces that are acting. So we've got a UDL here, so we consider the UDL as being a point force acting down in the middle of that UDL, don't we? And then we've got the 20 kilonewton force acting down at a distance of 2 meters, another point force of 20 kilonewtons acting at 5 meters, a UDL here of 20 kilonewtons per meter over a distance of 3 meters, so that'll be 60 kilonewtons altogether, that we take as acting in the middle, so that'll be at this point here. And then we've got the reaction force at B acting upwards at that distance, and then one more point force acting down that way at 10 meters. And so we sum all those moments together. So the sum of the moments about A equal, the first one will be this UDL, so it's 10 kilonewtons per meter over a distance of 2 meters, so altogether that will be 2 times 10 is 20 kilonewtons. So we replace this with a 20 kilonewton force acting in the middle at the distance of 1 meter. So that will be 20 times 1. And because it's acting clockwise, it will be negative. So it's minus 20 times 1. And then we go along, doing each one in turn. So write down what the moments are for each of the other point forces and this other UDL. So if we do that, adding up these, we get these other moments, all negative. The only one that's positive is the reaction force at B, going anti-clockwise. So we add them all together, all these negative values, we get minus 1020 plus 8 bar B must equal 0, because the sum of the moments equals 0. So therefore, the reaction force at B equals 1020 over 8. Okay. 127.5 kilonewtons. Kilonewtons because in our initial problem the force was measured in kilonewtons. So that's the reaction force at A. So now to find the reaction force at B, we repeat the process. Okay? The sum of the moments at B must equal 0, taking again this as being positive, anti-clockwise as being positive. So we go back to our diagram. Now we're looking at this point. And we consider this time we've got some distances going this way and some this way. So the first thing I would do is take into account this one. Again, if I'm using anti-clockwise as being my positive, then this force is going to be acting clockwise, so that will be negative. This force will be acting anti-clockwise, so that will be positive. Again, I've got this UDL, so this time it will be a distance of 1.5 meters from B, and so on. So moving along this way, work out all these forces. Again, this reaction force at A will be acting upwards, so that will be a positive. Negative, because we're taking anti-clockwise to be positive, aren't we? So work out what the sum of the moments of that B is, and calculate the reaction force at B. So if we add up all the moments for each of the components as we go along here, you should agree with these. So then we add them all together, taking into account the negatives and positives, we get 340 minus 8RA. The sum of all those moments must equal 0, so therefore 8RA equals 340 and RA equals 340 over 8, which is 42.5 kilonewtons. Okay? So reaction force at A equals 42.5 kilonewtons. So in our diagram we can put a reaction force here of 42.5 kilonewtons. And at B, we can put on a reaction force at B of 127.5. There's a check we can do now to make sure that we've done these calculations correctly. What would that be? Yes, our check is the total downward forces, the sum of all the forces acting downwards, in other words, 10 plus 20 plus another 20 there, plus 20 plus 60. All the downward forces must equal the upward forces, which are our reaction forces. So just quickly add up the total downward forces and all the upward forces and check they are the same. Yeah, we find the total upward force is 170, the total downward force is 170. Okay? That's a useful check. We could have taken a shortcut. We could have worked out what the reaction force was at A, 42.5, and then just subtracted that from 170 to get the reaction force at B. But if we made a mistake in this part of the calculation, we wouldn't pick that mistake up. So I would always recommend that you work out the moments for both and then use that as a check. I think you can be fairly confident now that those reaction forces are correct because they add up to 170. Now we can sketch the shear force diagram. We know that at A we've got a reaction force of 42.5 upwards. So we can go to a diagram, a sketch here, and at this point, at 42.5, we can show our force of, so we've got 42.5 kilonewtons at that point. And then at that point a UDL comes into effect. A UDL of 10 kilonewtons per meter is going downwards, so that's going to tend to reduce the force, and it's going to do that until by the time we get to this point here we've gone down 2 meters times 10 kilonewtons is 20 kilonewtons, so we've dropped by 20 kilonewtons by the time we get to this point. So if I subtract 20 kilonewtons from 42.5, I'll have 22.5, so I can say that we've reached 22.5 here. And how was that stress reduced? Linearly. So we can show a straight line going down. Now we can say we've got a point force of 20 kilonewtons acting down at this point. So it goes down rapidly by 20 kilonewtons from there. So it drops by 20 kilonewtons to 2.5. So we get to 2.5 kilonewtons here. And we can make a note of that point is 2.5 kilonewtons. And then nothing happens. No more forces are applied between here and here. So we can just carry along in a straight line till we get to this point at the 5 meter mark. So we move along. Then we drop by 20 kilonewtons. So 2.5 take away 20 minus 16, 17.5. We're just sketching it, but we can make a note of the points, minus 17.5 kilonewtons. And then our UDL applies over this distance here. We've got to be careful at this point because we've got point source inside the UDL loop. So I'm going down at the rate of 20 kilonewtons per meter for 2 meters. So that's 20 times 2 is 40, so I'm dropping 40 to this point here. So I go down 40 to minus 57.5. And how is it dropping? Linearly. And then it drops by another 10 to minus 67.5 at this point here. And then it drops by another 20 kilonewtons per meter, so another 20 kilonewtons to minus 87.5 by the time it gets to this point here. And then nothing much happens. At this point rather, we've got the reaction force of whatever it was, 127.5. So it shoots up to what's 127.5, take away 87.5, hopefully 40. Why hopefully 40? Because that's what's going to apply here, yeah, to bring us back down to, hopefully by the time we get to here, 0. So we're going to go up to 40, so it takes us back up to around about here somewhere. And then nothing much happens until we get to here, and then there's this reaction force, this downward force of 40 kilonewtons, and we're back to 0. So this is 40 here. So we sketched it. Now what I want to do is to plot this in autograph, and to be able to plot this in autograph I need to know the equation of that line so I can put it into autograph, and I need to then put that in only between 0 and 2 on this axis. So let's see how we go about doing that. Well, the equation of a line is y equals mx plus c, as you know, where c is the point at which it cuts the y-axis and m is the gradient. So what's the gradient of this line? I can calculate it, but actually I know it. I can calculate it by saying I'm going to measure this distance here. What the gradient between here and here. The first thing to recognise is that it's negative because it's a negative slope, and it's going down by 20 kilonewtons from 42 to 22.5 over a distance of 2 meters. So the gradient is 20 divided by 2, which is 10. But what is it that tells me that? I didn't actually need to do that. Where is that information? Right, yeah, the UDL is telling me, the gradient, it's telling me it's going down at the rate of 10 kilonewtons per meter. So this is telling me the gradient is 10. But don't forget it's a negative 10, because it's a negative slope. And the y-intercept, well, the y-intercept is here, because that's exactly where it cuts the y-axis. So what's the equation of this line for this particular part of the curve? And on my little notes I've labelled these, oops, I think points A, B, C, so you can actually talk about these lines. You might want to just label these points. So this is points C to D, and this is the line between D to E, and then we've got E to F effectively here. So just to enable us to do our calculations and show where the calculations are, when you're doing your portfolio task, you might want to set it out like that. So I know the equation of the line we're now working out is between A and B. So from A to B, the equation of the line is y equals minus 10x plus 42.5. What about B to C? What's the equation of that line? This line here. Y equals mx plus c is the general equation of the line. What's the gradient? Say again, Andrew? Naught, right. So there's no gradient, therefore 0x. It's just a constant. Y equals, what's the y-intercept? 2.5, right, yeah, if I extended this line back it would cut it 2.5. So in other words, the equation of the line between B and C is y equals 2.5, a horizontal line. What about C to D? Now the fun starts. The gradient's okay, isn't it? What's the gradient? Equation of the line, y equals mx plus c, but we know m, don't we? It's given by the UDL, yep, so it's 20 kilonewtons per meter, so it's 20. There. It's going down at the rate of 20 kilonewtons every meter. But don't forget it's minus 20, right? So we know that. The difficult bit, and this is why the fun starting, is finding C. Because if we look at this line here, that's this bit we're talking about, we're actually after if I were to continue this line back, where it cuts the y-axis. I want that point where it cuts the y-axis. So to find it, I need a point. I know two. I know that point, and I know that point. I just need one point on the line. I know two of them. I know that when x equals 5, in other words, this point here, when x equals 5, y equals minus 17.5. Or I could use when x equals 7, y equals minus 57.5. So I use that information. So when x equals 5, y equals minus 17.5, I think. Yeah. So therefore, y equals minus 20x plus c. I'm after c. And so I can now put in my values of x and y, 5 and minus 17. I know that minus 17.5 equals minus 20 times x, which is 5, plus c. So I can calculate c. Minus 17.5 equals minus 100 plus c. So c must equal 100 minus 17.5 and 82.5. So therefore, between C and D, y equals minus 20x plus 82.5. Okay, so now we've got the equation of the line for the first three parts of the stress-strain curve. A to B, B to C, and C to D. We've just got two more to go. D to E, this one, and E to F, this one. So I'll just pause this for a minute. You work out what the equation of the line is between D and E and F. So for D to E, again the gradient is minus 20, and just as a reminder, here it is, and so I've put on here in green how you can calculate the gradient. From C to D it's going down by 14 along 2, so gradient's 20 here, going down by 20 and along 1, so gradient's 20. But as a reminder, actually the UDL tells you the gradient, because that's the rate at which the stress is being applied. So we know the gradient's minus 20. Again, we need 2 points. We need when x equals something. So now let's take point D or E, it doesn't matter which. When x equals 7, which is at point D, y equals minus 57.5. So when x equals 7, y equals minus 57.5, which is this, sorry, D to E we're doing 67.5, not 57.5, 67.5. Whichever spotted that, minus 67.5. At D is 7 meters at the 7 meter point here. So then we just put those values in. So we've got the equation of the line, y equals minus 20x plus c. We're after c, so we substitute in our values for x and y. Therefore minus 67.5 equals minus 20 times x, which is 7, plus c. So minus 67.5 equals minus 140 plus c. So c equals 140 minus 67.5, whatever that is. There is a shortcut to this. We go back to the diagram. I was wondering if you'd see this. Here's my line, the C to D. Here's my line from D to E. The parallel, yeah. So this is just shifted down by 10. So if the y-intercept from C to D is 82.5, then yeah, 72.5. So we could have got that by a little bit of a shortcut, but I'm not unhappy that you've done this because you can see the idea. Okay, and then of course E to F, the last one, we've just got y equals 40 because it's a horizontal line. So y equals 40 for the last one, which is this bit, D to E. Sorry, E to F. There. So now we've got the equation of the line for each part. We've got the equation of the line from A to B, which is this. We've got the equation of the line from C to D, which is that. We've got the equation of the line from D to E, which is, I haven't actually written it down, so that will be y equals minus 20x plus 72.5. So that's that one. And then we've just written down the last one, e to f, y equals 40. Okay? So we can now plot these on autograph. So let me just show you this first one on autograph, and then you can try for yourself for the other ones. So firing up autograph, the first one I want to put in is from A to B, which is this one. So I'm going to plot the line y equals minus 10x plus 42.5 in autograph. So go to autograph, start a new page, y equals minus 10x, what was it, plus 42.5? 42.5. Now, I don't want it to go right the way across, I only want it to go between 0 and 2 meters. So what to do is start up options, and I want x to start at 0, so go to this box here. Thank you. Click on manual, yeah. You know better than me already. Hit the 0, and then you go to finish, hit 2, hit OK, hit OK, and it will plot the line between 0 and 2. Can't see it because it's probably off screen, so let's have a look, zoom out, and there it is. Okay. I can zoom in on the x-axis a bit because we're actually, let's drag it across to the left because I'm only interested in the the right hand quadrant here, and the maximum length of the beam is 10 meters, so I'm only interested in the 0 to the 10 bit, so let's zoom in on this bit. And then we've started to plot our stress curve. So now I want to plot the next line. So I'm plotting the line y equals whatever it was. So from B to C, y equals 2.5 between 2 meters and 5 meters, and then so on. So if I just pause this for a minute, if you just move on to autograph and see if you can plot these lines. Okay, so we should finish off with something that looks like this when you put all the lines in between the limits that are expected, and the handout that you've got has got those lines on it. Okay? So I'll stop those video now, and then the next video will be on plotting this moment diagram, which is what we're really after.